Hi everyone, today we're going to be going over problem 6a, which is the tree method for this recurrence. Recall that the goal of the tree method is to build up a summation for the total amount of work accomplished by this recurrence, but we break it down into small parts so that we can eventually build up that answer. Okay, so what's the first step? We're going to draw the recurrence tree. Recall that in the recurrence tree, every node represents a specific method call. And for each of these nodes, we keep track of the size of the input for that method call, as well as the amount of work that's done at that recursive call. So what does that look like? Well, we're going to do it with this specific recurrence. And remember that your top node, this is your first call for this recurrence. And your first call, the input is always going to start out as n. Okay, and then what's the amount of work? Well, the amount of work, we're going to take a look at our recurrence. And recall that our recurrence gives us a general expression. So it says whatever you plug in here, well, you're going to do 2 recursive calls on whatever that input was divided by 3 plus 5 times whatever that input was. And this represents that extra amount of work that you're doing in that method call. So therefore, the amount of work is 5n. Because our input is n, we directly substitute this, then we'll see that we'll do 5n amount of work. Okay, then we're also going to do 2 recursive calls. And we do 2 recursive calls on our n divided by 3. So for those 2 recursive calls, their input is now n over 3. Okay, now if the input is n over 3 in these recursive calls, what's the amount of work? Well, we'll look at the recurrence. And remember, because the recurrence is a general thing, we can directly substitute n with n over 3. So if we substitute n with n over 3, then the amount of work is 5 times whatever we just plugged in. So it's 5 times n over 3, 5 times whatever our input is. So therefore, the amount of work is 5n over 3. Okay, and then each of these nodes is going to do 2 more recursive calls on whatever their input was divided by 3. So they're going to do 2 recursive calls on n over 3 divided by 3, which is n over 9. So the input size for their resulting method calls is n over 9. And what's the amount of work? Looking at this recurrence, it's always 5 times whatever your input is. Our input is n over 9. The amount of work is 5 times that, which is 5n over 9. Okay, so usually we stop at 3 levels, and then we like to draw out the base case. So the base case is when we stop recursing. And when do we stop recursing? Well, we know that the amount of work at the base case is going to be 9. This is directly from the recurrence. We know automatically. And what is the size of the input when we reach the base case? It's the opposite of the recursive case. And if we recurse when n is greater than 1, then we're going to stop recursing when n is exactly equal to 1. So this is our recurrence tree. It's also important to note that you should be labeling the levels. And we start our first level at I equals 0. So I is the level number. And so we start out at 0, and then 1, and then 2, and then eventually we'll get to some level where we reach the base case. It's okay if you don't know the specific value yet, but it's important to start out by labeling the levels up here. And the reason why this is important is that we're eventually going to relate this level to the input and to the amount of work for any node in the tree. And this is what kind of the next parts help us figure out. Okay, so let's move on to part 2. What is the size of the input to each node at level I? So what is this asking for? This is asking for this top red number. We've labeled it in our nodes, so we just need to relate this level number, to this actual value of the input at each node. So you might have been able to tell from the way that we were just building this recurrence tree, as we could tell, whatever our input is, the next level, their input size is that previous value divided by 3. So we're dividing by 3 each time, n to n over 3 to n over 9. So because we're dividing by 3 at each level, the input at any level I is n divided by 3 to that I. Now, it's good to confirm this value. Another way that I like to go about these problems, if this wasn't super intuitive to you, that's totally fine. Another way to go about this is what I like to call the table method. And so what this involves is just building the table, right? We have some values that we want, right? For I equals 0, we want the input size to be n, and then when I is equal to 1, the input size should be n over 3. And then at level I equals 2, the input size for all these nodes is n over 9. So how can we express this in a generic way while relating I to this input size? Well, let's just look for a pattern. We can see that we're always having n and then divided by 3 to some power. And it increases as we get deeper in the tree. So it would make sense that we put I as the power of this 3. And so if we double checked this for each of these columns, we would see that this expression does express this pattern accurately. So this is really important that you check your work and you make sure that this expression actually works. And again, you can also confirm that by just going through the reasoning in the recurrence and seeing that we always divide by 3 on each level. So the input is always n over 3 to the I. All right, now let's go to problem 3. What is the amount of work that's done by each node at the ith recursive level? Again, what is this asking for? It's asking for this bottom blue number. For any level, how do we express that the work is like 5n and then 5n over 3 and then 5n over 9? Well, you might have also been able to tell from the way that we built this recurrence tree. It was always just 5 times whatever our input was, right? The amount of work at any node is just 5 times whatever your input is. And we know from this part, we just define that the input size at any level is just n over 3 to the I. Therefore, the total amount of work is just 5 times that. So the amount of work is 5n over 3 to the I. Again, you could use the table method to verify your answers, or if you didn't want to think about it this way, you could totally just do the table method and then come up with that general expression. Either way works. But again, you want to make sure that you verify your expression. All right, let's move on to part 4. What is the total number of nodes at level I? So this is asking how many of these boxes do we have at each level? How does it vary as we go down this tree? Well, first we start off with 1 node and then 2 nodes and then 4 nodes. And that's because we're making 2 recursive calls per node. So each one, it kind of doubles and doubles and doubles. So a good way to express this would be 2 to the I. As our I increases, then we get more nodes. And like I just said, we can totally use the table method here, and that would also be a good way to verify your answers. But ultimately, since our nodes double at each level, the expression is 2 to the I.
All right, hi everyone. So just picking up where Alison left off, we're going to continue working on 6A, working with this particular recurrence relation to find a summation for the total work using our tree method. So on part 5, we are asked for the total work done across the ith recursive level. So just looking at our tree, what we know is that our input at every level is given by n over 3 to the I, where I is equal to the particular level that we're working with. And then the amount of work we do at each level is given by 5 times n over 3 to the I. So, and also the number of nodes at each level is given by 2 to the I. And these were all determined in previous questions. So if you are unsure about how we got there, I recommend watching the video before this one where we work through them. But to find the total work done at any ith recursive level, we basically just multiply the number of nodes in that particular level by the work per node at that level. So like I just mentioned, we already know that the number of nodes in each level is going to be 2 to the I, and the work per node at each level is given by 5n over 3 to the I. So we can just simplify it together and we get 5n times 2/3 to the I. And that is going to be the total work that is done at every ith recursive level. All right, cool. So now 6 asks us, what value of I does the last level of the tree occur at? So to find out what value of I the last level of the tree occurs at, we have to think about a couple of things. So the first thing we need to think about is when our base case occurs in terms of what the input will look like. So we hit our base case when n over 3 to the I, which is the input, is equal to 1. So in other words, we hit our base case when n equals 1, and we know this because we can look at our recurrence relation. So looking at the recurrence relation, we do, the work is represented by this particular function when n is greater than 1. So in our otherwise case, that is when we will hit our base case. And the first time that we'll hit our base case is when n is less than or equal to 1. So we work with when n is equal to 1 will be the first time that we've hit our base case. So the amount of work done also to note is at our base case, we do t of n equals 9 amount of work. So Yeah, so we hit our base case when n over 2 to the I is equal to 1. And then what we want to solve for is this I value, which will give us the or the level. So we're just going to move the 3i over to the right, and then we're going to take the log of both sides because the inverse of the exponent is a log, and we want to isolate for this I. So this is the equation that helps us go back and forth between logs and inverses if you needed it. But what we end up finding is that the last level of our tree occurs at log base 3 of n. All right, so now we have that. And then we look at what 7 is asking for. So 7 asks for the total work done across the base level of the tree, or the base case level, or the last level. So we can go ahead and think about that. So just like we found the total work done at the ith recursive level, the amount of work done that is the total amount of work done in our base case is given by the number of nodes multiplied by the work per node, specifically to the base case. So we know that the number of nodes is going to be given by 2 to the I, and this is true for any level of our tree. And then the work per node in the base case level is given from our recurrence relation. So when we hit our base case, the amount of work we do is going to be equal to 9. So then we'll have 2 to the I times 9. And we also know when our last level occurs, what value of I. So right down here, you can see that I occurs at log base 3 of n, which we also just calculated in the previous part. So we could just substitute log base 3 of n for I up here, and this is what we'll get. So this 2 to the log base 3 of n times 9 is the total work that is done in our base case. All right, so now moving on to the very final part, we're going to take everything that we've come up with in these last few parts, all the building blocks, and put them together to get an expression for our total work. And that will come with a summation. So yeah, so our total work summation is made up of our recursive work and our base case work. And this is what our summation ends up looking like. So just to break it down a little bit, here's what's happening. So our recursive work is going to be this purple part, and our base case work is going to be given by this gold, mustard, yellow color. So this summation, we start at I equals 0, so right up here at the root, and then we go all the way up until the last level before our base case, so log base 3 of n minus 1. And what we're going to sum up is the amount of recursive work done at each ith level. So this is what we came up with in number 5. So we have 5n times 2/3 to the ith power. So in other words, basically what we're summing up is the number of nodes at that particular level multiplied by the amount of non-recursive work done at each level. And this is just a simplified version of looking at it. But in the base case, we can see the distinction a little more clearly between the number of nodes given by 2 to the log base 3 of n multiplied by the total amount of work done per node. So that is going to be given by 9. And then when we sum it together, we'll get our total work summation. And yeah, that is question number 6.